To some solar car performance issues. There's a lot one to do with modeling a solar car. It pulls on virtually all the disciplines everybody's been involved with in engineering. From the electric side, from the mechanical side, from the aerodynamic side. And people have done great modeling of solar cars. There are a couple books around. There are two books in particular on solar car modeling. One we like is The Winning Solar Car. We actually have used this in a course where we built some modeling programs that I programmed before after the 2005 car. Unfortunately, we never had enough data since then on a car to fit the models and actually try to use them. There have been some other software developed that's going to has a lot more of the factors involved in car performance and predicting how a car will behave driving at given speeds than we're going to talk about here has been actually produced. But again, we've never had a chance to get enough data for a car to actually use it. Hopefully you guys will finish the car early enough this time so we'll have a chance to actually do it. So, the purpose here is, in solar car performances, we want to say, in a typical race, now this isn't a track race, it's all of the similar things happen. What's the purpose? Well, the purpose is to cover a given distance in a minimum amount of time. Okay? You've got typical legs you have to run, and you want to get there in the fastest time. Now, what happens is, you've got a very limited amount of energy. Once the race starts with a full battery, hopefully, the only place you get energy from is your solar array. And our old array with triple junction cells was approximately like a big hair dryer if you're taking sun in at noon. The new array you're going to build is going to be like a small hair dryer at noon, but not through the full day. You've got a very limited amount of power. So everything you can do to increase the car's performance is energy efficiency, and as the speeds it can go without using extra energy is critical. People go to the lengths of cutting off extra bolt heads to try and reduce weight, and we'll see where some of those things come in. It's a given that the majority of teams will overspeed at certain times. And we'll still discuss why that's bad. If you drive fast, you use a lot more energy to cover a distance than if you drive slower. So what happens is if you run out of energy and have to drop to a very low speed so you only have enough power to drive on what the array is producing, your distance covered for the day for the energy goes down. And we'll talk about that a little bit. A winning car is designed to be efficient, not fast. Top speed isn't an issue. I don't think I've ever seen a race in the last 10 years where going much faster than 55 miles an hour at any point in time was a major advantage. There have only been a couple situations, say at the last day of a race where there's a short run after a stop where you can start with a full battery, where that might be true. Ordinarily, high efficiency is critical. With the new race regulations of less powerful arrays and smaller battery packs, that's going to be even more true. A winning car must have great strategy. Again, we'll talk about when you drive too fast because you think you can. If you're wrong, you pay a tremendous price. Probably in the 2005 race, I fully believe we would have been at least 2 places higher, moving up to perhaps 3rd place, if we had driven slower on at least one of the days. We ran out of power driving into a headwind because people were trying to keep up with some of the cars that were running faster. And what happened was they ran out of power and basically had to stop and could do almost nothing because they were on an expressway. Okay, solar car performance, it's all about energy. It's all about energy transfer. And the main components, without talking about the losses to go at a given speed, come from power coming in from the array. Now, we'll measure that in watts coming in. The array, the battery, and the motor controllers are all on a common bus. So they're all just connected together, plus to the plus, the minus to the minus. So anything coming in from the array goes on that bus. If the motors are demanding more power than currently the array can supply, then that power will be taken from the battery. If the motors are actually taking less power than the battery can, than the array supplies. Some of that power to drive it will go to the motors. The other power will go into the battery. So all things kind of sit in parallel there. And it's a relatively efficient transfer, but there's some losses even there. There are losses in there because there's losses based on the wires. We looked at the wire gauges for the 2003, 2005 car, and we looked at the losses of various gauges of wires. The thicker the wire, the less resistance, the less loss in the wires. However, the bigger the wire, the greater the weight, so the greater rolling resistance. So you can do things like that and say, what's the optimal gauge wire that we want? You don't want wires as big around as your fist, virtually no loss, but way too heavy. Okay, so you've got power transfer. The motor controllers, and the motors on that end, are what drives you. So that's where the speed comes in. We go in and out of that because when you're driving forward and have to drive it, you're taking power from either the array or the battery or both. When you're regen, when you're trying to slow down using the motors as generators, power comes back. And of course, then it only goes to the battery. We'll talk about that conversion basically, but that's not a perfect conversion. All in all, you're converting kinetic energy then into potential energy back in the battery, and that potential energy has to be converted back into kinetic energy. I estimate that's about a 15% loss in your kinetic energy, which is better than zero loss when you do that. The other stuff we call parasitic losses. You've got fans to run, relays to hold open, turn signals to run, cameras, the rear view camera to run, all the controller boards take some power. There's also some parasitic losses coming off there that just are there to run the car. When one looks at power, one has to take all those pieces into account. And if you want an effective solar car, you really have to reduce power in all those areas. Now, let's talk about some of the performance issues. The big ones we'll talk about during this talk are aerodynamic drag and rolling resistance. We'll have a couple slides talking about those coming up. I'm also going to mention air leakage and try to convince you it's really critical to seal wheel wells and seal the edge around the canopy. I'll give you something that should be somewhat convincing on what that cost is. Another area is wheel well turbulence. We'll have a diagram in just a second of aerodynamic drag, but we'll mention that. And it's worse if you have open wheels. That's the worst of all situations. But it still can be very bad if you have wheel wells that have open sides to allow turning. What occurs in there is you get a lot of turbulence coming in, buffeting in and out. All that buffeting back and forth actually increases drag dramatically. Some people have estimated the drag and wheel well turbulence on some cars more or less equals the rest of the aerodynamic drag for a race for a solar car. It's fundamental to try to keep that down. The best idea would be to have just a slit at the bottom where just the wheel protrudes only. The difficulty of that is in your front turning, you still have to be able to turn the wheel and still have it go down there and do it. But having as little as possible wheel well turbulence is kind of a critical piece. Changes in elevation, you move up and down. Well, it's kinetic, it's potential energy, right? You convert potential energy to kinetic energy. If you're going uphill, you have to convert some of that energy you've got, energy of motion, kinetic energy, to potential energy. And when you're coming down a hill, you can drive that potential energy back to kinetic energy. What that says for a driving strategy is, if you've got a hilly terrain with a lot of small hills, what you want to do is you want to slow down going up the hill, and then when you go over the hill and come down the next one, allow it to speed up. Of course, in all circumstances, you never want to exceed the speed limit. There are intensive penalties for that make it not worthwhile.